Welcome back, everyone. So our next application of derivatives is this topic called related rates. In the last unit, we were talking about how derivatives can be used to model the rate at which a quantity is changing, which could be interpreted in a number of different situations. But today, this is the topic where we study a situation where there are maybe more than one quantity changing at a time, but the rate at which one quantity changes affects the rate at which the other one changes. Let's take a look at a real quick example of how this might happen. So we've all done this before. We've dropped a rock in a pond or in a puddle, and what we do is we notice that there's a single point where the rock hits the water, and then ripples start to form, and those circles get larger and larger and larger. Now, waves travel in water at a constant speed. So what's going to happen here is that outer circle is going to grow. The radius of that circle is going to grow at a constant rate. So in this particular scenario here, what we're describing is that after we drop the pebble in a pond, the radius of that outer ripple grows at 1 foot per second at a constant rate. So imagine that at the end, after the instant the rock hits the water, 1 second later, the outer ripple has a radius of 1 foot. After another second, that outer ripple has now a radius of 2 feet. And after 3 seconds, the outer ripple has a radius of 3 feet. And so that continues to grow and grow and grow. And so then, obviously, there's more than one quantity that's measurable in this scenario. We could talk about that if I knew the radius, I could find both the circumference and the area of the disturbed water around that one point. And both of those are measured by the radius. We know that the area of a circle from geometry is pi times the radius squared. And we also know that the circumference of a circle is pi times the diameter, or 2 pi times the radius. So in either scenario, if the radius continues to grow, so will the area. And if the radius continues to grow, so will the circumference. So in other words, the rate at which the radius grows will have an effect on the rate at which the circumference and area are growing, hence the term related rates. Because the rate at which one quantity changes is going to impact the rate at which the other one changes. Now, in our situation here, we're only going to talk about the area, so we're just going to scratch off this equation here, and we'll focus on the area equation. Here's an equation that would help you find the area of the disturbed water if I were just to stop the action here and measure the radius of that outer ripple. Then I could use area equals pi r squared and measure the actual area. But that would be measured in square feet. What I really want to know is the rate at which that area is changing, which would be measured in square feet per second. And so what I need to start with is an equation relating those two quantities, the area and the radius. And so if you think about it, normally we would write things like this. The area is a function of the radius, and we could even call it A of r, and have this be pi r squared. So now area is thought of as a function of the radius. And so if I know the radius, I can compute the area. Okay, but what I want to do this time is consider that the radius is changing, not being constant. The radius is changing per second. And so r is really a function of time. And so as I write the area again here, now this time I'm using function notation, so I really want to think of this as function r of t squared. So in other words, the radius is a function of time. It depends on time, because every second it's growing by 1 foot per second, which in turn then makes the area a function of time also, because it's like A of R of t, which makes area also dependent on the time. And so both of these are functions of time now. And what I want to find is the rate at which the area is changing. So in terms of calculus notation, that's an instantaneous rate. And what I want to find is A prime of t, the rate at which the area is changing at a particular moment in time when the radius is 4. Okay? Well, that r is not a time, that r is a radius, so we might first read into the problem that since the ripple grew at 1 foot per second, that when the radius is 4 feet, obviously at 0 seconds it was 0 feet, after 1 second it was 1 foot, after 2 seconds it was 2 feet. So we also know then it'll take 4 seconds for the radius to become 4 feet. But I want to find the derivative of the area at the time t equals 4. So what I'm going to have to do here is take the derivative of both sides of this equation. So I'm going to apply the derivative, but not with respect to r or x. These are functions of time, so we're taking the derivative with respect to t. So the derivative of a of t is a prime of t. The derivative of the right side, with pi being a constant, and then this side we would have to use the chain rule because there's a function within a function here, 2 times the radius function to the first power times the derivative of r. Okay, now it's typical that we don't use the function notation all the time here, so I could just change a prime of t to something and use this notation here, dA dt, the derivative of a with respect to time. Here I could write 2 pi, and instead of r of t, I could just write r, and then instead of r prime, I could use r prime, but I could also just write dr dt. And so now I've got an equation involving the rate of the area and the rate of change of the radius and the radius itself. And so notice, to solve the problem that I'm going to solve here, I want to find the rate at which the area is changing. So I want to find this given that the radius is 4 feet and it's changing at 1 foot per second. So I can tell from the context of the problem that we're going to solve this at the instant the radius is 4, and we're told the derivative of r, or the rate of change of r, is always 1 foot per second. And I can now evaluate the right-hand side by putting those numbers in. 2 pi times the radius, 4 feet, times the rate of change for the radius, 1 foot per second. So now the numerical value of this is 2 pi times 4 times 1 would be 8 pi. And the label is what it should be, because I'm going to have feet times feet per second, which is square feet per second. Which, if you think about it, makes sense because we're finding the rate of the area. The area is measured in square feet and the time is measured in seconds. So this makes sense that the rate of change of the area will be measured in square feet per second. And the numerical value is 8 pi, or you can multiply it out on the calculator into a decimal. Okay, so just to summarize, we're studying the rate of change of the area of a circle with respect to time, but it has to do with the rate of change of the radius. So I started with an equation that involved the area of the circle and the radius of the circle. I understand that the area and the radius are both functions of time, so my derivatives are with respect to time, and that means that I use the chain rule, especially on the right-hand side. So the derivative of a of t is a prime of t, or I could write it as dA dt. The derivative of pi r squared is 2 pi r, so the first, times the derivative of r. Because remember, r is a function of time, so we need to use its derivative also. And now my answer is 8 pi feet squared per second. Let's look at some general guidelines for solving related rates. Here's some general guidelines that we definitely followed in the first example. First, the problem we read was about the pebble hitting the water, forming ripples, and we were told the rate of change of the radius, that it was growing at 1 foot per second, and we were asked to find the rate at which the area is changing. So we identified all the given quantities and the ones to be determined. I even made a sketch of the circles, circular ripples. We wrote an equation for step 2 that involved the variables whose rates of change were given or to be determined. So in the example, I started with the equation area equals pi r squared, because we understand that's how the area of a circle is related to the radius. Then we used the chain rule and differentiated with respect to time. So I took the derivative of a, and I took the derivative of pi r squared. And that resulted in the equation dA dt equals pi times 2r times the derivative of r. And I wrote the derivative of r, dr dt. And that was based on the chain rule. And then after completing that derivative, we substituted in quantities that we were told. It said find the rate of change of the area when the radius was 4 feet, and given that the radius changes at 1 foot per second. So we were told that the radius was 4, and we were told that dr dt was 1. And then I plugged those numbers in, and I was able to evaluate the right-hand side into a single number, and then that was equal to the quantity to be determined. But very important, we only substitute given numbers into our equation once we have differentiated it. If I were to do that ahead of time, if I were to put the 4 in here in step 2 and just written area equals pi times 4 squared, you're now treating the area like it's all a constant whose derivative would have to be 0. We know it's not 0 because the area is changing along with the radius. So we always reserve putting in numbers into our equation until I have found its derivative. Now, the only exception to that would be if you know a quantity is not going to be changing. And there will be a couple instances where you might understand that a quantity is not changing and therefore it should be treated as a constant. Well, let's look at another example problem and see if we can solve it too. So similar to the first one, this time I have a geometric situation again. I've got a large spherical balloon that we're going to inflate by pumping in 3.5 cubic feet of air per minute. We're supposed to find the rate at which the radius is growing when the radius is 2 feet. Well, you might not know the equation that relates the volume of the sphere to the radius. So in that case, I'm probably going to give this to you, and I'm going to give it to you here. From geometry, we know the volume of a sphere is 4/3 times pi times the radius cubed. That's the common formula for the volume of a sphere. What we want to find is the rate at which the radius is growing. So what we want to find is the rate of change, or the derivative of r, with respect to time. What we're given is the rate of change of the volume. We're pumping in 3.5 cubic feet per minute, and that is the rate at which the volume is changing. We're also told to solve this problem exactly at the instant that the radius is 2 feet. it's understood that the balloon initially was empty, so the radius would be 0. And as we fill it with air, it's going to grow. Both the radius and the volume will grow. And so we're going to be analyzing the rates at which they both grow and then stopping and seeing what the instantaneous rate is exactly when the radius is 2. So the next step is to take this function and find the derivatives of both sides. So I'm going to apply a derivative with respect to t to both sides. And on the left side, then, that gives me the expression dv dt. On the right, we notice that 4/3 pi is all a constant. I'm now going to write that as 4 pi over 3. And now we're going to take the derivative of the radius cubed. Now remember, r is really r of t. If we wanted to use function notation, it's r of t, function of time. So the derivative of this requires the chain rule to take the power down first, decrease the power to 2, and then multiply by r's derivative, which I'm going to denote here, dr dt. So now I've got an equation involving the rate of change of the volume, the rate of change of the radius, and the radius itself. And let's go ahead and simplify some things a little bit first, because the right side has some things to simplify. I've got 4 pi over 3, but then I'm multiplying right away by 3. So really I can cross out those 3's and write 4 pi times the radius squared times the rate of change of the radius, dr dt. Now let's remember what we were asked to find. We were asked to find dr dt given the volume's rate is 3.5 and the radius is 2. So we're going to put 3.5 over here on the left side. The radius is 2, so 2 squared is 4, and then 4 times this 4 is 16. And then I don't know the rate of change of the radius. That is what we were asked to find. So to solve for dr dt, we're going to have to divide by 16 pi. So dr dt is 3.5 divided by the quantity 16 pi. Now that expression really doesn't have a lot of meaning. I think we should just divide this on our calculators to figure it out. So I'm going to do that right now, 3.5 divided by 16 pi. And I got that this is equal to about 0.0696 or 0.070. Now let's think about the units here. The 3.5 was in centimeters cubed, or sorry, feet cubed per minute. Okay, but then we divided by 16 pi, and that would be measured in square feet because the radius was in feet and then it was radius squared. So cubic feet per minute divided by square feet should leave you with just feet per minute, which makes sense because this is the rate of change of the radius. The radius is going to be measured in feet and the time is measured in minutes. So this is our instantaneous rate of change of the radius, 0.070 feet per minute.